So what if you could predict future sales just by looking at one simple number? Or get this, save millions of dollars just by optimizing the size of a cardboard box. It sounds like magic, right? But it's not. It's a fundamental tool for finding hidden relationships in data. And in this explainer, we are diving deep into the power of simple linear regression.
But before we get into the nitty-gritty, we've got to start with the right mindset. And honestly, the statistician George Box just nailed it with this quote. The world is, well, it's messy. It's infinitely complex. And trying to model it perfectly is, frankly, impossible. But here's the secret. Our goal isn't perfection. The goal is to build something useful.
So that really is the big question, isn't it? How do we take all this messy data and turn it into something clear, something that can actually help us predict what's coming next? Well, the very first step is just understanding what we even mean by the word model. When we talk about modeling something, all we're really doing is creating a simplified version of it. And you know what? It's a skill we all use every single day, probably without even realizing we're doing it. This is such a perfect example. Think about it. A subway map completely ignores streets, buildings, parks. I mean, in that sense, it's totally wrong. But for its specific job, getting you through the subway system, it is incredibly, incredibly useful. A statistical model does the exact same thing, but for data. It ignores all the noise so it can show you the path. Okay, so how does this idea apply to data? Well, every predictive model is basically a story about a relationship. And like any good story, you need at least two main characters. In our world, we call them variables. At its absolute core, a statistical model is like a mathematical rule. It makes a really clear statement. It says, I believe I can predict what Y is going to do just based on what X does. We're literally defining the relationship between them. And here they are, our two key players. On one side, you've got the independent variable, or X. Think of this as your input, the thing you can measure or even control. On the other side is the dependent variable, Y. That's the outcome, the thing we're trying to predict. It's really that simple. We use X to predict Y. All right, enough with the theory. Let's make this real. We're going to see how this works with a hands-on example. So let's meet Armand's Pizza. Okay, so Armand has a super practical problem. He wants to open new pizza shops near college campuses, but he needs to know how much money can he really expect to make. He has this hunch that more students equals more sales, but, a hunch isn't really a business plan. He needs data. So what does he do? He gathers data from the restaurants he already has. The student population, that becomes our X, our predictor. And the quarterly sales, that's our Y, the thing we want to predict. And as you look at the table, you can kind of start to see a pattern emerge. In general, it looks like more students, more sales. So our mission now is to take this cloud of data points and draw one single straight line right through it that captures the overall trend the best. The fancy name for this is the least squares method. Basically, it finds the one line where the total distance to every single data point is as tiny as possible. Think of it like the most democratic line. It's the best compromise for all the points. And boom, after running the numbers, the analysis spits out this little magic recipe. This equation right here, this is our model. And you'll notice the Y has a little hat on it. We call that Y hat, and it's super important. It means the predicted sales, not the actual ones. So our model predicts sales will be 60 plus 5 times the student population. And this is where the math becomes an actual business strategy. That number 60, that's our baseline. The model is saying, hey, even with 0 students around, you'd probably make about $60,000. But the number 5, that's the real engine of our prediction. It means for every extra 1,000 students in an area, sales are predicted to jump up by $5,000. All of a sudden, Armand has a seriously powerful data-driven tool for scouting new locations. So we've got a model, and it looks pretty good. It feels right. But how much should we really trust it? Is this thing a Nobel Prize-winning insight, or was it just a lucky guess? We need a way to grade our work. Asking this question might be the most important step of all. I mean, a model is totally useless if you don't know its strengths or its weaknesses. So let's find out. Did Armand's model get an A+, or is it more of a C-? Here it is. Here's the grade, 90.27%. Okay, that definitely looks like a high score, but what in the world does it actually mean?
This number is called R squared, and you can pretty much think of it as the model's report card. So sales are different at all of our Mons locations for a ton of different reasons, right? Well, R squared tells us what percentage of those differences we can explain just by looking at the student population. And let me tell you, an R squared over 90% is, well, it's fantastic. That is an A+ on the report card, for sure. It means that the number of students by itself explains over 90% of why sales are different from one place to another. The other 10%? That's just noise. Stuff like local competition, how visible the store is. But for a model this simple, that is an incredibly powerful result. Okay, predicting pizza sales is cool and all, but does this simple idea actually scale up? Let's go from a small business to one of the biggest companies on the entire planet, Walmart. So Walmart had this absolutely massive logistics problem. We're talking hundreds of thousands of packages flying out of their warehouses every single day. And even tiny little mistakes with their cardboard boxes. A little too big, a little too small, maybe the wrong shape. It was all adding up to literally millions of dollars in waste. So what did they do? You guessed it. They used the exact same tool we just learned about. They built a simple linear regression model. Their independent variable, x, was the volume of a box. Their dependent variable, y, was how much the material for that box cost. They found the line of best fit to predict cost from size. And the result? By using that simple predictive model to get their mix of box sizes just right, they saved an estimated $2 million a year. This is what happens when you find that relationship that's just hiding in your data. It's not just some academic exercise. This stuff has a massive, real-world impact. So let's wrap this up with the key takeaways. First, we learned that models are just useful simplifications. They're like a subway map for our data. Second, regression gives us a recipe, a formula to predict an outcome, our y, based on just a single input, our x. And finally, R squared is that all-important report card that tells us exactly how much we can trust the story our model is telling us. And that really leaves us with one final thought. Now that you've got this basic idea down, you can start seeing these potential relationships, well, everywhere, from your company's sales data to the numbers on your personal fitness tracker. What patterns are just sitting there, waiting to be discovered? What future could you predict with just a simple straight line?